I am Dr. Rajiv Mishra from Indian Institute of Technology, Patna. Topic of today's lecture is a task offloading based on LSTM predictions and deep reinforcement learning. Content of this lecture: we are going to cover the joint decision making problem for cost optimization, that is cost minimization in IoT edge computing is modeled and is taking into account various processing latency, energy consumption and task throw rate. Using this we will discuss a predictive offloading algorithm which is based on the deep reinforcement learning and long short term memory. This particular algorithm, that is predictive offloading algorithm, predicts the edge server's load in real time and allocates the resources in advance, thereby improving the accuracy and that is the convergence accuracy and the speed of offloading process. So, let us get started with the introduction of this particular problem setting. Now, modeling the problem of computing offloading in a multi-edge, multi-device computing scenario often is a nonlinear optimization problem. Moreover, the goal of task offloading is minimizing the long term cost in terms of latency and energy consumption. By predicting the characteristics of the tasks and edge server loads, tasks are dynamically offloaded to an optimal edge server. So, in the decision model, the prediction is combined with task decision to dynamically allocate resources for different tasks to further reduce the latency and improve the service quality. In summary, meaning to say that we are considering the computing or the task offloading in multi-edge and multi-device scenario. So, meaning to say, if you recall the architecture or the model architecture of the edge cloud, what you will find is that there are multiple devices at the lowest level, or let us say the layer number 1. These are all IoT devices. Now, the task of these IoT devices, because of constraints of battery or the energy and also the latency, these tasks are offloaded to the edge. Now, the edge is a multi-edge, maybe that it is not only single node, but multiple nodes are there. So, multi devices and multi-edge task offloading problem is around the goal of minimizing the long term costs in terms of latency and energy. So, the cost function is a function of minimizing the latency and energy consumption jointly. So, this is the aim of computing or a task offloading from IoT device to the edge. So, the edge we are considering here as multi-edge. Now, what is happening is that this particular task offloading is incurring latency of transferring the data from IoT to the edge for computation. So, it requires the network latency, that is in the terms of network latency is incurred, and also it requires some amount of energy. So, energy is also required here in the task offloading. So, how to minimize these two things, that is the overhead of task offloading is to be minimized. So, this is done with the help of the predictions. So, by predicting the characteristics of the task and the edge server load, why? Because so this is an edge server. So, this is an edge server load which is incurring at the edge, and also the IoT will now generate the task. So, there are two characteristics, that is the characteristics of the task which are being generated out of these IoT devices, and also the server load, the edge server load. There are two aspects, and these characteristics needs to be used in the predictions. So, once these characteristics of the task, incoming task at the user devices and the edge server load, these tasks are dynamically offloaded to the optimal edge server. If these two things are being understood, then using the way of prediction, they can be offloaded to the optimal edge server. So, therefore, in the decision model, the prediction is combined with the task decision to dynamically allocate the resources for different tasks to further reduce the latency and improve the service quality. Meaning to say that this particular task allocation or task offloading, if it is combined with the predictions, and then in that case it will further, there is a scope of further reducing the latency and improve the service quality. How that is all done, we are going to discuss this aspect in this particular issue. So, therefore, let us understand through the motivation that the task offloading can result in the additional transmission delays and the energy consumption that I have already stated in the previous slide. Therefore, this aspect into the task offloading, which is incurring the additional transmission delays and energy consumption, how this is be overcome, reduced to a minimum value. So, therefore, task offloading problem is modeled as joint decision making problem for cost minimization, considering the processing latency and energy consumption and task throw rate. Task throw rate means we will understand here this particular term with the help of that prediction models or the constraints based on this particular task or the computation constraints. If it is not met, then those particular kind of offloading will be of wastage, that is called task throw rate. So, the online predictive offloading algorithm often is based on deep reinforcement learning and long short term memory, that is LSTM. So, both of them is used to solve this kind of predictive task offloading problem. So, we are now formulating this task offloading as a predictive task offloading with using deep reinforcement learning, DRL and LSTM. Now, such a model which is from the deep learning and the machine learning, it has a training phase of this particular predictive task offloading algorithm. In the training phase, the algorithm predicts the load of the edge server in the real time using LSTM algorithm and improve the convergence accuracy and the speed of deep reinforcement learning in the offloading process. So, therefore, based on the characteristics of the edge server and the characteristics of the load happening, these two things are being used with the LSTM for making the predictions of edge server load and the incoming load in the real time, and using this the deep reinforcement learning based offloading will be now seen as improvement in terms of convergence accuracy and the speed of offloading process decision making. Whereas in the testing phase, the LSTM network will predict the characteristics of the next task, and the DRL decision model allocates the computational resources for the task in advance. So, if it is done in the advance, then it will reduce the response delay and improving the offloading process. Therefore, we are going to see that this additional transmission delay and the energy consumption is quite reduced with the help of LSTM based predictions, that is the prediction for the edge server loads in during the training phase, and in the testing phase it will be LSTM network will predict the characteristics of the next task. Now let us understand the system model. So the model is built on multi-terminal, that is multiple IoT devices and multi-edge network scenario. Now here let us understand that here we have to now consider that the terminal layers devices are denoted by different values 1, 2, 3 and so on up to m. So that is shown over here. So we say that these terminal devices are nothing but, let us say, the mobile devices or IoT devices which are m in number. So m different devices are denoted by a set of terminal devices. Now the element of this particular set is either an IoT device or a mobile device. Let us assume that it is a mobile device. So on each mobile device there exists a task queue and a computation queue, which is shown in this particular figure. So on a particular mobile device there exists a transmission queue, there is a task queue and a computation queue. So the task queue stores the transmission queue and the computation queue. So the transmission queue stores the task to be offloaded. So here those tasks which require to be offloaded on the edge will be stored over here. The computation queue processes the task locally, that is on the mobile device. Now we have to now consider the set of edge layer servers which are denoted by capital N. So that is n different edge server nodes are there. So there will be a mapping from the task transmission queue to the edge nodes. Now the multiple computation queues are included in each. Now every edge node will have the multiple computation queue in each edge server for parallel computation of the transmission queue offloading task. So here we can see this particular edge cloud system with a mobile device and an edge node is shown over here. So let us see about the task model. So that means for any mobile device the tasks are generated in different time slots and are identified by a particular time set, that is 1, 2, 3 and so on up to t. Now each arriving task is first stored in the corresponding mobile device task cache queue, and then the decision model gives where the task will be offloaded to be executed. Now for a particular time slot t, out of the total time, the new task is generated by the terminal device, and let us say that for that is m is denoted as this. So the task which is generated by the mobile device is defined as the task model, which has the following three components. The first component is the size of the task data, and the second component is called the computational resource required per bit, and the third one is the maximum tolerated delay of the task. So that particular task model has three different characteristics, and all these characteristics is defined under the task model. Now let us see about the decision model. Now when the terminal device M has a new task that we have defined in the previous slide in a time slot, the decision model has to give the offloading scheme, that is xt of m is either from 0 or 1. So that is indicates whether the current task is offloaded or not. So if xt of m is equal to 0, this indicates that the task is executed on the mobile device, that is local computation. Whereas if xt of m is 1, that indicate the task will be offloaded to an edge server. Whereas yt of mn, which is also from 0 and 1, represents the edge server to which the task is offloaded for the execution. So once it is decided the set of tasks which are to be offloaded to the edge server, then now the mapping of these tasks to the edge server is to be done in this case. So, therefore, this YTMN represents the edge server to which the task is being offloaded. So, M means mth task and N means that nth edge server where this particular thing will be offloaded. So, if YTMN is equal to 1, that is the task M is offloaded to the edge server N for the execution. So, the task in this model are atomic level tasks, that means they cannot be, they are indivisible. Now, each offloaded task can be executed in only one edge server, and the tasks offloaded to the edge server for the executions are often constrained by this particular equation. You see that the summation of all n is from this particular set if it is 1, and m is from, that is mobile, from the mobile devices set, and t is from time slot, and xt of m is equal to 1, that is it is decided that the task is to be offloaded. Now, computational model, that is called the terminal layer computing model. So, the task generated by the t time slot must wait until the computation queue is free to execute the computation. Therefore, the waiting delays are calculated in this particular manner. So, the processing delay in the computation delay is also being calculated, and if you calculate the total energy consumption of a particular device which is required for task to be executed locally is mentioned here in this particular equation. Now, the computational model, where edge layer computing model which we are now considering, the processing latency of the task at the edge layer is mentioned, and the completion time for the edge layer task is also mentioned over here. Total delay of the task on an edge server N is now mentioned. Now, energy consumption incurred when the tasks are offloaded to the edge server is given by this particular equation, and this denotes the waiting energy consumption, transmission consumption, and edge node computation consumption of the task respectively. Let us understand the goal. So, overall model of the system is a trade off between the time delay and the energy consumption of the task computation to create the minimization of a cost problem. So, the solution goal is to minimize the total cost of the task generated in the system over this period of time. So, let us see the prediction model, that is called a task prediction model. So, the decision process is required after the task generation, and there will be a certain time delay from the task generation to give this particular decision. Although the task generation is dynamic and random process, considering the long term nature of the task, it will have a strong correlation with the time. Therefore, based on the history of the user devices, we can predict the task that will be generated in the next time slot. So, that is the premise, that if we know the characteristics of that particular devices, so using that particular history and having a machine learning model, it can predict the task that will be generated in the next time slot. So, this is shown in this particular figure. Now, we can predict the information of the future task by the prediction model. So, therefore, we are discussing about task prediction model, and then determine the decision and allocate the computing resources upfront for that particular task. So, that is what is shown over here. Now, if we have a predictive model, task predictive model which is based on LSTM, then it can predict the next task information, and this will be used in making the decision. And if when a new task, when the real task comes, this particular prediction and the actual process, actual task requirement, both are now compared as an error, and if the error is within a particular bound, that is called a threshold, then we have to follow these decisions which we have taken beforehand using the prediction model about predicting the task, and therefore follow that particular task offloading based on the a priori decision making, and add this task information to the training samples and so on. If the error is not within the threshold, that means our prediction is going wrong, then in that case we have to put this new task information into the decision model to making the decision, and then follow rest of the other steps that is we have already taken. So, if the error is within the between the real task and the predicted task is within allowed threshold, the task is directly offloaded and computed according to the assigned decision information. Now, if this is done, then it is going to save time and therefore latency in terms of task allocation. So otherwise the offloading decision is given using the decision model, and the information of a new task is added in the historical data as the training samples. So by training the LSTM network, the weights and the biases of each gate in the network are updated to improve the accuracy of the prediction model. So that is quite important to understand that here in this particular problem we are using LSTM based task prediction model, and this particular task prediction model, that means is able to decide about the resources which are required for a new task to be arrived beforehand, and that task allocation is almost finalized provided it is the real task is the error is within the threshold. So therefore the load prediction model also let us see about that. So historical load sequence data is logged and used to train LSTM load prediction model. So the predicted idle server is obtained from the trained model using historical sequence data as the input. So the predicted idle server is used as the offload the computing node when the training the DRL. So DRL training process involves selecting the actions with a certain probability epsilon. Now when the random action is selected, the size comparison between the random value and the probability, that is epsilon, is used to determine whether the random action or a predicted action is going to take. So epsilon greedy approach is used here for exploration purposes, and otherwise it will be exploitation purpose. So using the prediction action and pre-selected idle server can reduce the number of explorations by the agent and improve the convergence in this particular offloading decision making. So offloading decision is illustrated over here. Now you can see that as far as the environment is concerned, LSTM based prediction model is used and it is able to predict upfront beforehand. Now this particular prediction action now as far as is used in the deep reinforcement learning. So the states of a deep reinforcement learning will now use the action. So there are two ways. So it uses an epsilon greedy approach in DRL. So it says that the values of epsilon, that means it is able to support exploration and exploitation. So let us see about the first part, which is called a model training. So the goal of DRL is to maximize the total reward by making the optimal actions. So DRL uses epsilon greedy strategies for exploration and exploitation. So exploration involves the random selection of any action with a probability in the expectation of a higher reward, while exploitation selects the action with the largest action estimate. So this stochastic strategy fully explores the environment state, but requires extensive exploration and a low data utilization. So therefore in the model, the action selection is the offloading decision of the task, with the action space known whether to execute locally or to offload to an edge server. So during stochastic exploration, LSTM is used to predict the load of the edge server and give an optimal action. So optimal server at the next time slot is predicted based on historical load situation to obtain a higher reward and avoid the edge server load imbalance. So let us see this particular model training phase. So there is a LSTM, and based on this historical load it will make a prediction, and this prediction is combined into an action, and this will be fed to the agent, whereas the entire environment is being captured as a part of the state and is given to the deep neural network for selecting that particular. So as I told you that this particular LSTM during the training process will take the information historical load of the edge servers, and based on that it trains this particular model of deep reinforcement learning here in this case. This training process is happening. Let us see the offloading process. So when offloading process, then LSTM prediction model uses the task record or a task history that will be from the mobile devices or from the devices. So, each mobile device will generate a different type of task at different time slots, and there is a system response delay to the task decision request and the waiting delay in the queue between the generation of the task and giving a decision. So, the H system processes the data from the mobile device and stores the process records. Based on these historical records, the feature information of the next arriving can be predicted by LSTM. So, this particular LSTM based prediction of the next task is fed to the state here in deep reinforcement learning. So, the predicted information is given to the deep reinforcement learning to make the offloading scheme for the predicted task. Now, when the real task arrives, the offloading decision is given directly if the error between the real task and the predicted task is within the allowed range, thereby improving the convergence time and thereby latency. Now, if the error is not within that allowed range, the decision is made according to the real task using the decision model, and this particular sample will be stored here for further improvement of that prediction model. So, this illustrates the offloading decision phase. So, here you can see that now this LSTM based task prediction model is fed, that is, it will predict the task information and that is given to the state. So, therefore, DRL using the predicted task is fed to the state, and then it will be evaluated based on the actual task arrival, and then the difference between the predicted and the actual is being used to measure with the help of a threshold. If it is within the threshold, then the predicted is more accurate, and whatever DRL has taken the decision. So, now let us understand more detail about the DRL. So, that is nothing but a deep queue network. So, typical deep queue network is often composed of agent, state, action and a reward. So, the policy is generated as a mapping from state to the action, of the states to the action to obtain the reward R. So, reward is given over the state, and a particular action denotes the reward that can be obtained by choosing the action in a given state ST. So, this particular reward function is used, and summation of all the rewards is a long term reward which is shown over here. Now, when the state space and the action space dimensions are large, then it is difficult to put these action space into the queue table in a normal reinforcement learning situation. Now, to solve this, the deep queue networks model in a DRL combines a neural network, also deep neural network, and with the queue learning algorithm, and therefore, this queue table are put into the queue networks, uses the neural network to fit the optimal queue functions. So, therefore, there are two neural networks with the same structure, but a different parameter in DQN. One is called target network, the other is called the main network. Both are being maintained simultaneously. Now, when iteratively updating the network, the algorithm first uses the target network to generate the target queue values with a label f of t, and uses the loss function to update the parameters of the main network. So, you just see that the target network and the main network both are used at the same point of time here in maintaining the queue values, and these parameters are updated in the main network. So, after the introduction of the target network, the target queue values are generated by the target network remains constant in time, which can reduce the correlation between the current queue values and the target queue values and improve the stability of this particular algorithm. Now, let us see about the use of replay memory in this algorithm. So, in order to break the correlation within the data, deep queue network uses the experience replay method to solve this problem. So, after interacting with the environment, the agent is stored in the replay buffer in this particular form. So, you can see that state at a time t, action t will make the next state, and the reward at a time t. So, when executing these valuation updates, the agent randomly selects a small set of experience tuples from the replay buffer, and then the algorithm updates the network parameter by optimizing this particular loss function. So, using experience replay can not only make this training more efficient, but also reduce the problem of overfitting that generates during by the training process. Therefore, it is proposed to solve this overfitting or overestimation problem with the help of double DQN. So, DQN takes the maximum value with the maximum each time, and the difference between this maximum value and the weighted average value will introduce an error, and this particular error will lead to a overestimation after a long time accumulation. Therefore, double DQN is composed of two networks, QA and QB, that we call it, utilizes these two networks to proceed the state valuation and action output alternatively. That is, one network is used to select out the action and the other network is used to update the Q values according to the selected action. So, double DQN makes this learning process more stable and reliable by separating two steps of selecting the action corresponding to the Q value and evaluating the Q values corresponding to that particular action. This eliminates the overestimation brought by the greedy epsilon greedy algorithm and obtains more accurate Q estimation. So, instead of finding the label values of the parameter update directly from the target network, double DQN finds the action corresponding to the maximum Q value in QA and then uses this selected action to compute the target value and update in QB. Now, dueling DQN compared to the DQN, dueling DQN considers the Q network into two parts. The first part only relates to the state S and specific action to be adopted, has nothing to do with this part and called value function apart. Noted by this second part is related to both state and action, and this part is called action advantage function. So, all these things is expressed using an expression of a Q values. Now, let us see about the decision model elements here in this case. So, agent means that each mobile device is considered as an agent that selects the next action according to the current state of the environment and improves the ability of the agent to make the decision by continuously interacting with the environment. So, the goal of the agent is to make the optimal action at any state and thus minimizing the total cost in this edge computing system. Whereas, as far as the states are concerned, at the beginning of each time slot, each agent observes the state and it includes the properties of mobile device, that is waiting queue state, the transmission queue state, and the bandwidth information and the real time load of the edge nodes. All are the states and are closely related to the action to be selected by the agent. Let us see about the action. So, based on the current state, the agent first decides whether the newly generated task needs to be offloaded for the computation or not. If it needs to be offloaded, it chooses which server to offload. It also chooses the appropriate transmission power when offloading the transmission. So, all these are part of particular action. Now, let us consider about the reward function. So, reward, after observing the state at a time slot t, the agent takes an action according to the policy and that receives a reward at a time slot t plus 1. So, while updating the scheduling policy network to make the optimal decision at the next time slot. So, the goal of each agent here is to maximize its long term discounted reward by optimizing the mapping from states to action. So, the agent tends to make this optimal decision in its continuous interaction with the environment. So, the reward function is therefore shown here in this particular manner. So, the entire online predictive task offloading algorithm is now put together here, and let us discuss about that. So, input is that input different task at each time slots, output is optimal offloading decision and the total cost. So, you have to initialize QA, QB and S and initialize the replay memory D to the capacity N. Now, for each episodes from 1 to M, now we need to do initialize the sequences and pre-process the sequence. Now, for each time slot T, we have to now use the probability 1 minus epsilon to select a random action or a LSTM predict action and generate another random number. So, that random number is, if it is greater than epsilon, then a random action is selected, that is ST, and if it is less than epsilon, then predicted action selection is done. Otherwise, select an action such that it will be the maximum of that Q value QA, maximum of QA, or it is B, then it is, if it is in B, then it is maximum of or B is equal to maximum of QA here in QB. Now we have to execute the action AT and receive the reward and the next state, and this will be stored in the replay memory. Now randomly sample this mini batch of the action experience from D and then perform the gradient descent on a loss function with respect to the network parameter. Now then we have to choose A, which is based on the QA network or and QAB network, and observe the value of reward function and S prime or the next state. Now if update A is done in this Bellman equation, and if you update B, then you will follow this Bellman equation, and this particular algorithm now you can understand that it uses the LSTM based task predictions here. Now let us see this particular kind of problem, how experiments will be done. So lot of data sets are available in public. So let us see that we use a data set using the Google cluster information, which includes the information about the arrival time, data size, processing time and so on, and therefore considering the following simulation parameters which are available in the literature. So this particular task prediction for this kind of problem which are available in the literature is shown over here about different values, and the training process of LSTM and DRL we have already explained. So when performing the training on DRL, so it will offload the decision model, and it takes a longer time to explore and select the better result due to the initial random selection action of the agent. Now we predict the server load based on the H server record history, and based on this prediction results, the server predicts to be non-ideal is selected with a certain probability as the offload choice for the next moment. So therefore you can see that there are two different historical data sets are maintained, whether it is at the training phase or at the testing phase. So this solution allows the agent to effectively avoid selecting the servers with a high load, and thus reducing the task processing latency and task dropping rates. Now here LSTM is used for load prediction and compare the impact of decision with the load prediction, that is LSTM plus DRL, and without LSTM only DRL is used for offloading. So if you compare, you will find that there is a good amount of possible reduction in or overcoming from the two problems which we have stated, that is latency and energy. Now as a result, DRL is significantly slower than LSTM and DRL for load prediction in the early stages of the training. After certain training, the average delay, energy consumption and the number of throw is reduced rapidly using LSTM for the load predictions. Impact of the task numbers are also studied here. So that means if you consider the data set T is equal to 100, 200, 500, 1000 and compare the performance of DQN with the double DQN, dueling DQN, your optimal prediction algorithm under different time slots. So what you will find that the system will increase the number of time slots increases. So this predictive task offloading will reduce its latency on an average by 6%, and offloading cost is also reduced by 25%, and task drop rate is also reduced by 31%, which is quite substantial, and therefore compared to the other algorithm, the cost, average latency and the task drop rates are quite improved with the help of LSTM based prediction model. So now let us see about the impact of learning rate. Now study the convergence of the algorithm at different learning rate. So the algorithm is able to achieve a relatively fast convergence rate and a small convergence cost. Now let us see some numerical analysis of this LSTM based predictions. Suppose you are managing a data center that provides a cloud computing services to the customers, and now you use a LSTM model to forecast an hourly CPU utilization of the data center within the next 24 hours in order to optimize this resource allocation and minimize the energy consumption. Now then, if you have the data set with the hourly CPU utilization data for the last 1 year, which contains, let us say, 8760 data points. So you must choose the first 7000 data points for training and the remaining 1760 data point for validation. Then you set the batch size to 64 and the number of epochs to 50. Now assuming that the model takes 5 seconds to process one batch of the data on a GPU, so how long will it take to train the model? Now this question assumes that the data has already been pre-processed and formatted into the LSTM model. So let us see the problem solution, which is going to give you the insight into this numerical calculations. So the time it takes to train the model can be calculated in this manner. So batch size, if you keep 64 and the number of training points, let us say you keep 7000, number of epochs 50 and the number of iterations per epoch. So that is nothing but the number of training data points divided by the batch size. It comes out to be around 109, that is number of iterations per epoch. So the number of iterations is equal to number of epochs into number of iterations per epoch, that is 5450, and time taken to process one batch of the data on the GPU is 5 seconds. So the total time taken to train the model will be 5 multiplied by the batch size multiplied by total number of iterations, that comes out to be 20.4 days for full fledged convergence based training. Therefore, it will take approximately this much of days to train the LSTM based model using the given data set and batch size and the number of iterations over here. Now let us summarize this entire lecture, that in this lecture we have considered the computational offloading problem, which is very important in bringing up this edge computing. So this optimization objective is to minimize the long term cost by jointly optimizing task latency, energy consumption and task discard rate. So the model combines this, that is a prediction model of LSTM networks and the decision model of DQ network. So this prediction based algorithm, that is task offloading algorithm, which is based on deep reinforcement learning, has the advantage, if let us say that you combine it with double DQN and dueling DQN. So that means advanced level of advanced models or more complicated complex models are at advantages. So the training speed and accuracy of deep reinforcement learning models are quite improved with the help of LSTM prediction capabilities. So this particular algorithm reduces the offloading decision delay of the task in the actual inference model. So therefore this can be taken forward in the development of edge computing and therefore will improve the performance in the real IoT applications with the help of edge computing. Thank you.